once you grasp that concept, it changes everything about how you look at the night sky.
It really does. So tonight, go outside, look up, and try to see the whirlpools instead of the empty space. So what if a purely theoretical physics paper about, like, the fundamental shape of the universe just accidentally handed us the exact blueprint for deep space colonization?
Yeah.
Oh, and planetary defense system to go along with it.
Right, just threw that in there.
Yeah, exactly, because if you're listening to this deep dive, you've probably wondered how humanity is ever going to practically manage, the massive infrastructure required to actually survive in deep space. And today, we might actually have the answer to that.
It genuinely reads like the setup to a hard sci-fi novel, right?
Right.
But the stack of sources we're pulling from today, it's grounded in really dense math, established physics, and incredibly detailed patent filings. I mean, we are looking at a massive paradigm shift in how we measure the universe.
Yeah, welcome to the deep dive. So today's mission is to unpack this groundbreaking 2026 theoretical preprint. It's by Christy Seeley, and it's on recursive partition cosmology.
Right, RPC.
RPC, yeah. But we aren't stopping at just the theoretical math, because alongside it, we have this joint U.S.-Canadian patent disclosure. It's by Seeley and Brad Yoakum, and they basically take that exact math and turn it into hardware.
Yeah, which is incredible.
It is. They call it the QLAG System. So that's the quantum Lagrange array gravitational interferometer.
Quite the mouthful.
Right. But we're going to explore how rethinking the absolute fundamental geometry of space itself leads directly to this completely autonomous quantum navigation system, and ultimately a solar system-wide burglar alarm.
Yeah, and to even begin visualizing this, this solar system-sized machine, we first have to understand the physics that essentially demanded its invention.
Right, the why before the what.
Exactly. We have to start with the why. So in recursive partition cosmology, or RPC, the foundational premise is that space is not an empty container.
Okay.
In the standard model that you and I grew up with, we think of space as this static stage where physics happens,
Not a
right?
big empty box.
Yeah, a box. And the actors are the particles, the planets, the stars. But RPC argues that space itself emerges from what the author calls a recursive conserved partition.
I'm struggling with the visual here a bit. If space isn't a pre-existing container, but it's somehow made of these, dividing fractions, how does matter actually move through it? Is space a physical substance?
So think of it more as a macroscopic quantum superfluid.
Okay.
The theory asks you to imagine a single normalized substrate. Just picture it as the number one, a hole.
Right.
Then it divides. It recursively partitions into distinguishable states. And as it continuously divides to create more and more distinct states, counting those states gives us what we experience as entropy.
Wait, hold on. Entropy isn't just things getting messier inside a room that already exists.
No.
The actual accumulation of that entropy is the room. That is what creates the volume of space.
Yes, exactly. That is the ontological inversion at the heart of the paper. Space is simply a macroscopic property of accumulated entropy gradients. Right. And where this gets incredibly interesting is the geometry of it all. As this quantum substrate recursively divides to, pack these new states together, it attempts to form geometric structures in 3 dimensions.
Okay.
But it hits a fundamental mathematical wall. It's the phenomenon the paper calls partition frustration. I have to say, I love that term in physics. Right.
It assigns this almost human struggle to the actual fabric of reality.
It's a very fitting descriptor, actually. RPC relies on this geometric truth if you try to pack regular tetrahedra. So picture 4-sided pyramids made entirely of equilateral triangles, right?
Get it.
If you try to pack them together in 3D space around a single shared edge, you can fit exactly 5 of them.
Okay.
But those 5 tetrahedra take up about 352.6 degrees of the available 360 degrees.
Oh, so they don't perfectly close the gap.
Exactly. They leave a gap of exactly 7.356 degrees.
I was reading that in the math section and trying to picture it. It's like trying to perfectly tile your bathroom floor with pentagons.
Yes. Great analogy.
You can try as hard as you want, but you cannot do it without leaving awkward gaps between the tiles.
You literally can. And in RPC, those gaps, those frustrations, they aren't just mathematical quirks that you can round down and ignore. They are the actual engine of physical reality.
That's wild.
Yeah, the broader implication of that 7.356 degree gap is that it physically prevents the universe from locking up into a rigid, brittle crystal.
Oh, because it can't ever perfectly settle.
Exactly. The failure to pack perfectly creates stable defect structures within the macroscopic quantum superfluid. And when you scale those defects up to the cosmic level, the paper argues those stable swirling defects are what we call galaxies.
That completely wrecks the old rubber sheet analogy we all learned in high school.
Oh, it destroys it.
Yeah, because if I'm following you, gravity isn't a dent made by a bowling ball on a trampoline. Gravity is the inherent geometric tension of a universe that can't quite fold its corners perfectly together.
Right.
It's the tension of the superfluid trying to close an unclosable gap.
You're hitting on the crucial mechanism there. The attempt by the universe to continuously resolve that geometric incommensurability creates a tension gradient. And that pull across the cosmological superfluid is gravity.
Okay, I think I'm actually wrapping my head around this.
But here's the catch. To definitively prove this framework over the standard model, the paper points out that you need to measure the second sound velocity of this cosmic superfluid.
And I'm guessing you can't just build a tabletop experiment in the university basement to do that.
Not even close.
No, you would need a measuring cape the size of the solar system.
Which brings us out of the theoretical realm and straight into the second document in our stack, right?
Right, the QLAG System patent disclosure.
Yeah. This is where we get into some of the most staggering engineering I have ever seen proposed. I mean, how do you actually build a quantum measuring tape across millions of kilometers of deep space?
Well, you start by building a network of Bose-Einstein condensate stations, and you deploy them precisely at the 5 Lagrange points of the Sun-Earth system. Okay, I have to pause you there because the location choice really stood out to me. Why Lagrange points specifically?
Good question.
Like, why not just put these nodes in a standard Earth orbit? It would be infinitely cheaper to launch, and if something breaks, we could, theoretically send a surface mission to fix it.
Sure, the economics definitely favor Earth orbit, but the physics absolutely forbid it.
Oh, yeah?
Yeah, it all comes down to the heart of these stations, the Bose-Einstein condensate, or BEC. A BSC is a macroscopic quantum state.
Okay.
You take a cloud of atoms, and the patent specifies rubidium-87 for this, and you cool it down to less than a microkelvin above absolute zero.
Wow. So basically as cold as the universe gets.
Yeah, exactly. At that extreme temperature, the atoms lose their individual thermal identities. They collapse into the exact same quantum ground state, basically sharing a single global wave function.
So it's kind of like a choir where everyone is singing the exact same note in the exact same pit with the exact same breath. It stops being a group of individuals and becomes one giant unified voice.
That is a perfect way to think of it. But that giant voice, that shared quantum phase, is exquisitely fragile.
Right.
If you place that system in Earth orbit, it experiences the Earth's gravitational gradient.
Meaning gravity is pulling harder on one side than the other.
Exactly. Gravity is just a tiny bit stronger on the bottom of the satellite than it is on the top. And that microscopic difference creates phase noise. It scrambles the choir. It destroys the quantum coherence almost instantly.
Ah, I see. So the Lagrange points aren't just convenient parking spots. They are an absolute operational requirement.
They are the only viable locations. The 5 Lagrange points, L1 through L5, are specific orbital coordinates where the gravitational pull of the Sun and the Earth perfectly balance out the orbital centrifugal force. The effective gravitational gradient vanishes entirely. It is what physicists call a force-free environment.
Wow.
You have to place the delicate Bose-Einstein condensate in those perfectly still gravitational waters so it can survive without being torn apart by phase noise.
But L1 and L2 are, what, like 3 million kilometers apart? Yeah, roughly.
And L4 and L5 are separated by hundreds of millions of kilometers. How on earth do you connect a delicate quantum state across that kind of staggering void?
You obviously can't string a physical fiber optic cable between them.
No cables. You utilize what the patent calls BEC entrainment nodes.
Okay.
The system doesn't try to stretch a single massive condensate across the void. Instead, it creates a quantum bucket brigade.
A bucket brigade.
Yeah, between the main Lagrange stations, you deploy a series of intermediate nodes. These nodes overlap their matter wave functions just enough to pass the phase coherence along.
Okay, I follow that. But space is full of hazards, right?
Oh, absolutely.
So what happens if a node gets hit?
Well, each node uses a hydrogen or rubidium-MASER, which operates like a laser, but emitting microwaves, to actively maintain the quantum phase.
Okay, I read that part and got completely stuck. How does a microwave beam fix a disruption? Like, let's say a stray cosmic ray strikes one of the nodes. How does the maser actually help?
Well, when a cosmic ray hits a node, it deposits energy and knocks the quantum phase out of alignment. Going back to your analogy, the choir loses the beat.
Right, someone sings off-key.
Exactly. The maser driving field acts as a rigid, unyielding metronome. Because the maser is locked to a specific, highly stable frequency, it aggressively rephases the condensate, basically forcing the atoms back into lockstep with the rest of the network within fractions of a millisecond.
Oh, so the maser is basically the choir director slamming a baton on the music stand, forcing everyone back on tempo before the whole song falls apart.
That's a great way to picture it, yeah. And because these intermediate nodes continuously pass this rephased coherence down the line, node by node, they maintain a distributed, continuous quantum state across millions of kilometers without ever needing a physical conductor.
That is just, okay, so we have this giant, perfectly synced quantum web stretching across the inner solar system. But at some point, a human being needs to look at a computer screen and read the data. You have to extract that delicate quantum information without collapsing the whole system.
Exactly. And the heavy lifting there is done by the terminal transducers at the main stations utilizing Josephson junctions. Specifically, they use squeepides, superconducting quantum interference devices.
I mean, you really can't beat the acronyms in theoretical physics. Squee-wide.
They do love a good acronym.
But the patent mentions they use something called parametric transduction. That sounds like incredibly dense jargon. What is the actual mechanism happening there?
So, a Josephson junction is basically two superconducting materials separated by a microscopic insulating barrier, and they are unbelievably sensitive to phase differences.
Okay.
The challenge is, as you said, if you measure a quantum state directly, you destroy it. Parametric transduction gets around this by measuring the phase dispersively.
So it's like a highly skilled translator. The translator can listen to a microscopic, fragile whisper and seamlessly type it out in large, bold font on a screen for everyone to read, but they never actually interrupt or disturb the person who is whispering.
The translator analogy captures the dispersive nature perfectly. The squeed reads the microscopic quantum phase difference of the condensate and imprints it onto a classical microwave carrier signal.
Oh, wow.
It translates the quantum state into a loud, classical radio broadcast that standard digital signal processors can easily read. So what you are left with is a continuously updating measurement of the exact space-time geometry and the exact gravitational potential between any two stations in the solar system.
Okay, now that this completely silent, invisible quantum reference grid is blanketing the solar system, the most immediate problem it solves for you isn't abstract physics. It's the fact that our spacecraft are basically flying blind in the dark.
Yeah.
I think most people imagine deep space navigation as this hyper-advanced, flawless GPS. But the reality is incredibly messy, isn't it?
It really is. The current reality is a massive logistical bottleneck. Deep space navigation relies entirely on the Earth-based Deep Space Network, or DSN.
Right.
If a probe is heading to Mars, that probe is effectively blind. It doesn't actually know its own coordinates. Earth has to ping it with a radio signal, wait for the signal to reach the probe and bounce back, calculate the time delay and the Doppler shift, and then transmit a message telling the probe where it is.
It's like trying to navigate a dark forest by shouting back to base camp and waiting an hour for the echo to tell you where to step next.
Yes, and that delay is brutal. At Mars opposition, that light travel latency can be up to 80 minutes round trip.
Oh.
To make matters worse, that radio signal has to pass through the solar wind, which causes plasma dispersion, so it blurs the signal. On top of that, the classical atomic clocks on board the spacecraft experienced oscillator drift.
Oh, they tick out of sync.
Exactly. They slowly tick out of sync with the clocks on Earth, so the probe is constantly accumulating navigational errors.
But the QLAG system seems to bypass all of those issues simultaneously.
It changes the paradigm entirely. Because QLAG establishes a persistent, absolute, quantum coherent inertial reference frame, a spacecraft no longer needs to talk to Earth to figure out its location.
Right.
It just needs to carry a compact onboard BEC-MASER receiver.
It just passively tunes into the local broadcast.
Exactly. The onboard receiver phase locks to the QLA microwave carrier frequency broadcasting from the nearest Lagrange nodes.
Wow.
Because that phase grid is absolute and intrinsically tied to the gravitational geometry of the solar system, the spacecraft instantaneously deduces its exact position and velocity. autonomously.
That's incredible. I was looking at the accuracy projections in the patent, and they are wild. The current Earth-based tracking gets us to about 10 meters of accuracy at the distance of the moon, right?
Right.
QLAG brings that down to sub-millimeter accuracy, and it maintains that precision no matter how deep into the solar system you fly.
It is literally the end of getting lost in space.
It brings an infrastructure far superior to your phone's GPS to the entire inner solar system.
And the operational freedom that gives to deep space missions, it really cannot be overstated. You no longer need to book limited time on the Deep Space Network dishes just to keep a probe on course.
That's a massive leap forward. But, okay, if the system is sensitive enough to track the mass of a single tiny spacecraft moving through the void, it must be able to feel other, much larger things moving in the dark, right?
Oh, yes.
Which brings us to the ultimate burglar alarm: planetary defense against astronomical impact threats.
Right. The planetary defense application fundamentally solves the biggest flaw in our current early warning systems. Because right now, asteroid defense relies almost entirely on optical reflectivity. We use telescopes to scan the sky, hoping to catch sunlight bouncing off a rock.
Which works great if the asteroid is made of shiny metal or highly reflective ice.
Exactly.
But space is pitch black, and a significant portion of comets and asteroids are essentially giant lumps of dark charcoal.
Dark, non-reflective objects have an incredibly low albedo. They are practically invisible against the backdrop of space.
That's terrifying.
It is. Historically, we often don't spot these dark objects until they are already deep in the inner solar system, sometimes after they've already crossed Earth's orbit. It's a huge blind spot.
But QLAG doesn't care about light or reflectivity. It uses gravity.
Yes. The patent details how the system measures the tidal tensor.
Okay, what's that?
It's a differential acceleration along the baseline between two nodes. If any object with mass enters the space near a baseline, its gravity pulls slightly more on one node than the other. The network feels the gravitational mass directly.
So it's like holding a tightrope in the dark. You don't need to actually see the acrobat to know they've stepped onto the rope because you can instantly feel the subtle change in tension in your hands.
That tightrope analogy is the exact mechanical principle of the tidal tensor. The system registers the tension change. For example, the patent states that a 100-meter dark asteroid, which is roughly 10 to the 12 kilograms, produces a differential acceleration on the L1-L2 baseline that the network can detect from 1,000,000 kilometers away.
Now, I have to play devil's advocate here because 1,000,000 kilometers sounds like a vast distance to someone sitting on Earth.
Sure.
But in astronomical terms, that's practically our front porch. If a comet is screaming toward us at 50 kilometers a second, 1,000,000 kilometers of range only gives us roughly an hour of warning.
Right.
That's barely enough time to sound the alarms, let alone coordinate an entire deflection mission. Right?
Your math is spot on, yeah. And for small, incredibly fast objects, an hour might be all you get.
Oh, yeah.
However, the detection sensitivity scales non-linearly with the mass of the threat.
No.
A 100-meter rock might cause local devastation, but a 1-kilometer class asteroid the size that causes severe global climate disruption triggers the sensors at 30 million kilometers.
Oh, wow.
That gives humanity days or even weeks to respond. And for a 10-kilometer extinction-level object, the system detects the mass billions of kilometers out.
That's huge.
You would have months or years of absolute certainty, even if the object absorbs 100% of the light that hits it.
Okay, that context helps a lot. It scales with the severity of the threat. We might take a localized hit from a small, fast rock, but we won't go the way of the dinosaurs without seeing it coming.
Exactly.
But the patent also details threats that aren't just giant rocks. It dives into detecting dark gravitational anomalies and interstellar shockwaves.
This part is fascinating. When a nearby star goes supernova, the initial events travel at the speed of light. We see the optical flash immediately, and our detectors catch the neutrino burst.
Right.
But the actual physical destructive force of the explosion, the magnetohydrodynamic or MHD shockwave of compressed interstellar gas, travels much slower, usually between 10,000 and 50,000 kilometers per second.
So the physical shockwave could arrive decades or even centuries after we watch the star explode in the sky.
Yes, and when that wall of compressed gas finally hits our solar system, it aggressively compresses the heliosphere. If it's strong enough, it can strip away planetary atmospheres.
Wait, really?
Yeah, the patent actually references research suggesting a nearby supernova shockwave likely contributed to the end Pliocene marine extinction event on Earth about 2.6 million years ago.
Wow. And QLAG is sensitive enough to see an interstellar wave of gas coming.
By continuously measuring the gravitational perturbations at the outer edges of the solar system, out near the heliopause, roughly 100 astronomical units away, the array can detect the massive bulk of the compressed interstellar medium pushing against our neighborhood.
That is wild.
The math in the disclosure shows it would give Earth a definitive 3-month early warning before the shock wave disrupts the inner heliosphere.
3 months to harden our global electrical grids, move vital satellites into safe configurations, and prepare surface shielding. It literally downgrades a civilization-ending event into a highly stressful but manageable logistical crisis.
When you consider the sheer scale of that warning system, the implications naturally bleed past our own solar system. It treats our entire stellar neighborhood not as a collection of isolated planets, but as a single monitorable volume of space.
Which perfectly sets up the final section of the patent deep space colonization. How does this quantum grid secure our species on a galactic scale? Because it seems like the ultimate foundation for humanity leaving the nest.
Well, if humanity successfully deploys QLAG in the Sun-Earth system and proves the architecture, it becomes our interstellar template.
Okay.
When our first colonization efforts reach other star systems, places like Alpha Centauri or TRAPPIST-1, the absolute first piece of infrastructure we would deploy wouldn't be habitats. It would be a local BEC-MASER network at the Lagrange points of those new stars.
So they immediately establish their own local GPS and planetary defense alarm.
Exactly. But the vision goes much further than isolated local networks. The patent outlines how we can technically bridge these separate stellar grids.
Really? How?
By utilizing advanced optical atomic clocks and time delay laser interferometry, we can phase compare the microwave carrier signals between the star systems.
Hold on. Time delay laser interferometry. How does shooting a laser bridge a gap of multiple light years to sync a quantum phase?
So, the optical atomic clocks at each star system provide an incredibly precise timestamp.
Okay.
By firing highly stabilized laser pulses between the systems and comparing those timestamps against the local phase data, you can computationally correct for the years of light travel time.
Oh, I see.
You effectively lock the phase of the Alpha Centauri network to the phase of the Earth network.
Wow. When you link those signals, you're effectively turning the empty space between stars into a single galactic-scale quantum interferometer.
The entire volume of space between the colonized stars becomes part of the measurement grid.
The societal shift it creates is profound. Whenever we talk about interstellar colonization, it's always framed as a fragmenting process.
Right.
Ships leave, and they are essentially cut off by the vastness of the void, totally isolated from Earth.
Right, relying on messages that take years.
Exactly. But this architecture creates a unified infrastructure. It ties humanity together with a persistent, unbroken quantum thread. It turns the terrifying unknown of the galaxy into a contiguous, mathematically predictable, navigable space.
It fundamentally solves the tyranny of distance and isolation. Because the phase reference is absolute and universally synced, a colonization ship halfway between here and Sirius always knows its exact relation to both homes.
Wow.
It enables safe, autonomous, and coordinated deep space logistics on a scale we've only ever seen in science fiction. It is the literal highway system for a multi-stellar civilization.
We've covered an immense amount of ground today. We started by looking at a highly abstract math problem, like why can't you pack 5 tetrahedra perfectly into a 3D space?
Yeah.
Tracing the implications of that one geometric gap, that frustration, led to a physics theory that redefines gravity. And that theory birthed a patent for a quantum grid that will guide our ships, track extinction-level asteroids, warn us of exploding stars, and eventually tie galactic civilization together.
It really is the ultimate end to information overload.
Oh, totally. We stop trying to track every individual object in the sky with radio dishes, and instead we turn the absolute geometry of the solar system itself into our single data source. We just listen to the tension of the web.
And that tension is never static. It is constantly updating, constantly trying to resolve the fundamental geometric incommensurability of space.
Which perfectly brings us to a final, staggering claim buried right at the conclusion of Seeley's RPC paper. A thought to leave everyone with today as you digest all of this.
Yeah, this is the big one.
If this theory is right, and the math holds up, and it successfully builds this interstellar network, it implies that the standard model of physics has been looking at the universe backward this entire time.
Exactly.
According to the author, the universe isn't expanding in a straight line into nothingness. It's rotating, it is actively cycling to resolve its own internal geometric tension.
Yep.
And what we look up and call galaxies, they're just quantized vortices. They're the whirlpools in a giant spinning cosmic superfluid.
Once you grasp that concept, it changes everything about how you look at the night sky.
It really does. So tonight, go outside, look up, and try to see the whirlpools instead of the empty space. So what if a purely theoretical physics paper about, like, the fundamental shape of the universe just accidentally handed us